y, so we need to rewrite it as an exponential function. So x equals e to the y is that exponential function, and then the radius is going to be that function because it's the outer function. Then we can integrate usually from pi r squared, so from 2 to 1. Because we're doing it vertically, y1 to y2, so ey squared dy, and then we integrate that using u sub, and we get pi 1/2 e to the 2y. Evaluate and get pi e squared divided by 2 e minus 1.
All right. Anyone has different answers or any comments? Great. Okay, thank you, Kaiser. Next one. I think it's Carlos. Carlos 1. Then after Carlos, Angel 5.
Yeah, yes.
Angel 5. Then Alexandra 10. Kaiser, I see you. Not Kaiser. Carlos, I see your screen.
Okay, sorry for the delay.
It's okay.
Okay, so this is question 1, and the question is.
We lost you.
Sorry?
You came back.
Okay. Okay, so we had to sketch first to know what we had to do. So we put y equals 0. We sketched x equals 1, x equals 2. There, just right here. And then we had to sketch the line. And this is our sketch. And this will be the area we're trying to find between x and 2. And this is our disk. Okay, first we had to find a first by, as seen before, pi radius to the second power, and we replace the r by the line of the equation that we had up here, and we get say we get pi parentheses 4 minus 2x plus x to the second power divided by 4. Then we have to use our equation by finding the volume and integrating from 1 to 2 as in here. And power divided by 4. X to the, and by finding the derivative, we get 4x minus 2x to the second power divided by 2 plus x to the third power divided by 12. And then we have to integrate, find 1 to 2. We replace 1 for all of our x's and 2.
Okay.
Minus, this is 1 to the second, I'm sorry, the 1 divided by 12 minus 1. Okay, so that's everything.
Okay. So right, Carlos, your voice is on and off. But anyway. All right. I'm
sorry, I don't know if you heard me.
Yeah. But basically, so in the end, your answer is 19 over 12 pi, right? Okay. Anyone has different answers? Anyone has any comments? All right, thank you, Carlos. Angel, next one, 5. Alexandra, 10.
I'm sorry, Professor. I don't know if you were able to hear me while I explained.
Yeah, it was on and off, but it's okay.
Oh, okay. Sorry
Yeah,
about that.
somehow, right, it's not, it's okay. Yeah, it happens.
Thank you.
This is Angel's, I see Angel's screen. But I don't hear you, Angel.
Hello?
Yeah, I hear you now.
Okay. So we are asked to find the volume of the solid obtained by rotating the region bounded by the given curves above the specified line. And then we also asked to sketch the region, the solid, and the typical disk or washer, which I did right here. And so first we find the cross-sectional area of the washer, which is equal to A area equals pi outer radius squared minus pi inner radius squared. And then I found the outer radius to be x, y equals x, determined by y equals x, and the inner radius determined by y equals x cubed. So I just plugged them in and found pi x squared minus x, that is 6 for the cross-sectional area. And then we find the intersections to get the lower limit and the upper limit. And to find b, I set them equal to each other, the two functions, and solved for x. I found x to be 0, 1, and -1, and the lower limit will be 0 and the upper limit will be 1, since it says there that x should be greater than or equal to 0. So a would be 0 and b equals to 1. Then we find the volume, which is equal to the integral of the cross-sectional area evaluated from 0 to 1. And then we take pi out of the integral since it is a constant, so we get pi times the integral of x squared minus x to the 6. Oh yeah, so this pi shouldn't be there. Oh. And then we find the antiderivative and evaluate it from 0 to 1. I found the antiderivative to be x cubed over 3 minus x to the 7 over 7. Yeah, and evaluate from 0 to 1 and simplify until I get 4 pi over 21.
Okay, great. So 4 over 21 pi. All right, anyone have any questions? Okay, good job, Angel. Thank you. And next one, Alexandra, right? 10. Yeah, Alexandra, I see your screen.
Good morning.
Yeah, good morning.
Okay, are you able to hear me well? Okay.
Yeah.
So for number 10, we had to solve for 3 equations around y equals 2. So then I graphed it.
Hold on one second. What do you mean solve
right
for
here.
3 equations? No, what are we trying to do
sorry?
here? I heard you were saying you are trying to solve 3 equations.
Oh no, I'm sorry. I meant graph 3 equations.
Oh,
so
graph
right
3
here.
equations. Okay, great. Right.
Yeah. Yeah, and the dotted line here represents what we're rotating around. I had to do some research on this question because it's not about the x or the y-axis. So I found that you do still do pi r squared, but r is represented as, in this case, the outer function minus d, and d would be the value of whatever the graph would be rotating about. So d would, in this case, equal 2. So the outer function would be e to the negative x, and the inner would just be y equals 1. So over here, I represented from the interval from 0 to 2, pi.
Hold on 1 second.
bracket.
Can you show us the region before rotating?
Oh, yeah. Yeah.
Yeah,
Okay.
can you show me the region?
This is the region it's rotating.
Or the oval shape? No, shaded area you are rotating.
This part.
So you have y equals to e to the negative x, which you have the graph already. So the region is bounded by those 3 equations, right? Your y equals to 1 and the x equals to 2, right? Yeah, so that's the region you're rotating over y equals to 2. So can you show the other part when you rotate? Oh, right. Okay, you're making this circle scene, you're rotating this piece.
Yeah.
So can you draw the other piece?
It would look something.
Yeah. You can draw a line there, right?
Something
Y equals to 3.
this. So, and then this would be the other region.
Great.
Kind of reflect, this would reflect the other region.
Right. Great. Yes. Perfect.
Okay.
Yeah.
So I represented the interval from 0 to 2, since this is up to x equals 2, the last function in pink. So the outer function would be e to the power of negative x minus 2, because 2 is what represents d, and then the upper function would be 1 minus 2 squared. So then I just simplified this part below, and then right after that I found the antiderivative. This portion is just me simplifying e to the negative x minus 2 squared, and then I found the antiderivative of negative 4e to the negative x, which I found to be 4e to the negative x. So then I found the antiderivative of this part, which is 4e to the negative x minus half e to the negative 2x plus 4x. And then the antiderivative of negative 1 is just negative x, bar 0 to 2. And then I simplified this entire thing. I really just did 4x minus x, which would be 3x here. And then since this is from 0 to 2, I plugged in the value of 2 for the function, subtracted by the value of 0 of the function, and then simplified all of that here. And then I combined these two for the last simplification, and then I just added I subtracted 6 minus 4 plus half to get 5 over 2, and this was my final answer in blue.
Okay. Anyone has a different answer? Or anyone has any comment? All right. Okay. Good job, Angel. Thank you.
It was Alexandra.
Oh, Alexandra, I'm so sorry.
Yeah, it's all right.
Alexandra. Sorry, my bad. All right, let's see who's the next one. Stanley, right? Angel, Alexandra 10, Stanley 3. Yes, Stanley, I think I see your screen 3.
Hello.
Yeah.
So I tried to find the volume of x equals 2 to the square root of y, and they also gave us x equals 0 and y equals 9 about the y-axis. So then for this, the radius is just 2 to the times the square root of y squared times pi, which I got is pi times 4y is area, and then the integral of 4y is 2y squared, and 2y squared, the limits of integration was 0 and then 9 because y equals 9. And then once I plugged it in numbers, I got 162, and 162 multiplied by pi to get the volume.
Okay, let's see your picture. So x equals 0, so it's bounded by x equals 2 radical y, so that's your region. And y equals to 9. Then rotate this piece over y-axis. I see. Okay, anybody has different answers? Any comments? All right, okay. Thank you, Stanley.
No problem.
Stanley, after Stanley, Ray 7. Yes, Ray, I see your screen.
Hi, hello.
Yeah.
Yeah, okay, so the picture's there. So for this one, first I find the y volume. So I use y squared minus 2y to 0. So I use a quadratic formula, so I got like 2 and 0. Then after we find the y volume, we use the integral to 0 pi and 2y minus y squared to the square dy. So after we solve that, we got like 4y squared minus y to the 4th power, and I enter derivative this and got 4y cubed over 3 minus 4 to the 5th power over 5, and I plug in 2, and I got like 0. I ignore supposed to be a minus 0, so I only solve for 2. And the answer is 64 over 15 pi.
Okay. All right. Anyone has different answers? Okay, you could use quadratic formula, or that's an easy way. You see, you can factor this. The y squared minus 2y, you can factor out y minus 2 equals to 0.
Right, yeah.
Then you use 0 property. Right away, you get this 2.
Okay.
Okay. All right.
All right.
Okay.
Thank you.
Thank you, Ray. Next one. I think it's Jason. Jason 12. Then Noella 2. Okay, Jason, I see your screen.
So we're trying to find the volume of the solid bounded by the curve x equals y and y equals radical x about the line x equals 2. First, we we find x because it's being rotated about the y-axis. So x equals y squared, and then we find the lower and upper limit. I set them equal to each other, and I got 0 and 1. So for this problem, we have to find the radius, and since we know like the radius from the outer radius to the to x equals 2 is 2, we set 2 subtracted by the inner radius, r1 and r2. So r1 is y squared, and r2 is y. And then we get this integral. So first I multiplied out 2 minus y squared, and 2 minus y squared. I got this integral. And then I basically combine like terms, and I got negative 5y squared plus y to the 4th power plus 4y. And then I got the antiderivative, which is negative 5y cubed over 3 plus y to the 5th over 5 plus 4y squared over 2. And then I plugged in 1. So when you plug in 1, you get negative 5 over 3 plus 1 over 5 plus 4 over 2. And I set all of the fractions to common denominators. I get negative 25 over 15 plus 3 over 15 plus 30 over 15. And then I solved, and I got 8 over 15. And the answer is 8 pi over 15.
Okay. Anyone has any comments? Good job. Thank you.
Thank you.
Noella, I see your screen.
Are you able to see my work, Professor?
Yeah.
So for this question, to begin with, when I first graphed it, I realized that because of the symmetry, we could simply double the volume and only calculate the volume from 0 to 1, and basically double.
Noella, my screen's gone somehow.
Okay, I'll re-upload it again then.
Yeah, it came back.
Okay, so as I was saying, when I graphed the equations that were the functions that were given, y equals 1 minus x squared and y equals 0, I realized that it would produce disks rather than a washer with no hole in between. So because of the symmetry, I decided to only calculate the volume from 0 to 1 and basically double it. So from there, I started by v equals integral 0 to 1 times 2 pi times 1 minus x squared times dx. And since 2 and pi are constants, that's why I took them out of the integral, which resulted in v equals 2 pi times integral from 0 to 1 minus x squared times dx. From there, I plugged in I figured out what 1 minus x squared would be, and that is 1 minus 2x squared plus x to the 4th power. From there, I solved for the antiderivative of them, which was x minus 2x cubed over 3 plus x to the 5th over 5. And then from there, I substituted the upper and lower limits. And then with further calculations, I got 8 over 15 times 2 pi, which resulted in 16 pi over 15.
Okay. All right. Anybody has any questions? I think these two, you see the second line, you have pi r squared. Maybe that's a type, right?
No, I think so. Pi r squared is the area, and that area is being squared. So that area is for each of the disks, and that's squared.
What do you mean? I do not understand now. Why we
So,
square the area?
so you see how it says 2 times pi r squared, and that's squared? So I took out the pi since it's a constant, and we're left with r squared. So from there, I substituted the function that was given as the radius and squared it.
Yeah, you don't need this square, right? You need r square.
Oh, yes, yeah.
Yeah.
It's
Okay.
just a small typo then, yeah.
Yeah, that's a typo, right? Okay. All right.
Thank you so much.
Any questions? Okay. Thank you, Noella. Let's see. Anybody else? Oh, Amir, you want to show 11?
Okay, Professor. So, for 11, we're given the problem y is equal to 1 plus secant of x. 1 second. And then we're also given that y is equal to 3. And also we're given that it's about y is equal to 1. So if we were to graph it, let me see. Okay. Let's do that. So it looks something like that, and then what you do is you would draw our lines. So we have your y equals 1 and y equals 3. So at 1 right over here and at 3. And we know that it's about, so 3 would be dashed. I mean, for 1 it would be dashed. And then what we would do from here is we're asked to find a given region. So we can only assume that it's one region since the volume would be infinity if we're looking for another. So what I did was I actually tested at 0.5 right over here. and then we would have a washer. We would have a washer style. So we would have an inner radius and an outer radius. So from here, 1, 2. And then all we would do from here is also, since we know these two equations are y, we can set them equal to each other.
Amir, can you shade the region?
You want me to shade the region?
Right.
Like everywhere or just like one part?
Everywhere from, so this is y equals 3, maybe just one part about y equals 1. 1 plus secant x.
Anyway, so we set the two equal to each other, and we get here secant of x is equal to 2. So from here we get that x is equal to plus or minus pi over 3. And then from our graph right over here we can see it's symmetric. So we could say that our bound is from 0 to pi over 3 for our upper and lower bound. So all we would do from here is we would find our two radiuses. So one radius we can clearly see that it's 2 to 1, so that's 1. So our radius 1, that is our outer radius. From y equals 3 to y equals 1, our outer radius, we can have that. And then we also have our second radius. So our second radius, that would be 1 plus secant of x, our function, minus 1. So that would equal secant of x. And then all we have to do from here is just find our volume. So our volume would equal, we would have the integral from, oh yes, so we would have your pi over 3 and a 0. And then we would also have here a 2 pi over here. And then all we would do is we would evaluate it. So we'd have this from 2 squared minus secant of x squared dx. And then all we would do from there is we would simplify. And you get that volume is equal to 2 pi. And we would have here from pi over 3 to 0. And then we would have your 4 minus secant of x squared dx. Because you're supposed to subtract.
Someone to try 9? Sure, get yourself ready.
Actually, no, it's a typo. It should be secant squared of x. Alright. And then we would have your dx. So then all we would do from here is we would evaluate. Actually, no, we would find the antiderivative first. So you would have your if we take the antiderivative, you'd have your 2 pi, and then we would have 4x minus tangent of x. So we have your 4x, and then we know secant squared x, that's tangent of x, the antiderivative. And then all we would do is we would evaluate.
Oh. Can you put back again?
I don't think I can, Professor.
Oh, right. So it just disappears, right?
So do you want me to just do the formula because I already did the graph?
Yeah, you already did everything. Just wait. Just tell us your final answer, because you so far you have from 0 to pi over 6.
Yeah. So I had two.
You just have to evaluate 4x minus tangent x.
Yeah. Can I just do that part quick? It's not that long.
Yeah.
So we have your 2x, and then we would have your 4x minus tangent of x. And then we just evaluate at 5 over 3 and 2. And then what we would get here, in the end, we would get here 2 pi times 4 pi over 3 minus square root of 3. And then we could just simplify this. So we'd have your wait, Professor, we can simplify it, right? Can we, or?
But just leave square root of 3. So
I mean the pi.
Pi square.
Would this be the answer to my second line, or would I have to simplify it?
You could leave like this. This.
Okay, so this is the answer then.
Right. I feel so weird about it. You have pi square appeared, right?
Well, that was the answer. I don't know.
Yeah, but anyway. All right. Anybody has any questions? So this question involves a lot. All right. Thank you, kids. Amir.
Thank you, Professor.
Thank you. And let's see. Ursa wants to show 9. Yeah, go ahead, Ursa.
Wait, Professor?
Yeah.
I think you skipped over me. I was supposed to present 8.
Oh, I'm sorry. Okay, after Ursa. Okay, I'm sorry.
Okay. Okay,
Good morning, Professor.
Good morning. I see your screen.
Yeah. So basically, we have two functions, which is y equals x and y equals radical x, and we're rotating on y-axis, which is y equals 1. And this is going to be a washer, meaning it's going to have an inner and the outer radius. The inner is 1 minus radical x, and the outer is 1 minus x, and it's minus 1 because it's rotating on the y-axis, on y equals 1. So the is basically the outer function minus the pi of pi times the outer function minus pi times the inner function. And then when we simplify, we get 1 minus 2x minus x squared and 1 minus.
Hold on a second, Ursa, before you go further. Okay, yes. So I see the region here. And can you tell us that after rotating the other part, can you draw the 3D picture?
Yeah, I'm gonna do it here. 1 second.
Oh, it doesn't give you a pen, right?
Can I write on this?
I'm not quite sure. Sometimes it's
So
weird.
basically, it's gonna be so it's gonna be shaded on the top, I think, right?
No, I'm asking you.
Not giving the pen.
Yeah, you can explain, right? You don't have a pen, but explain. Because you are given two functions, y equals x, y equals the square root of x. And those two functions enclosed, enclosed at 2 points. Right?
Yeah.
So,
So the
basically, I want
two
you to explain.
points are 0, x equals 0, and on x equals 1.
Why?
This is like the intersection.
Yeah, why? Can you tell us why?
Because it intersects on that.
Yes, they do intersect. Those two functions do intersect at 0, at 1. But can you tell us why?
Why they intersect?
Yeah. How do you know?
Oh, you could make them equal to each other, or you could graph.
Oh, okay. If you make them equal to each other, how do you solve from there?
So basically, you could do so x equals radical x, and then you simplify, meaning you factor the equations, and then make them equal to 0, and then find the 2x, which is x equals 0 and x equals 1.
How do you factor x and the square root of x? So you're thinking, so x equals to square root of x. Now you're making x minus square root of x equals to 0.
Yeah.
Okay, then what do you do?
Then you're gonna factor it.
Factor
So
what?
further simplify.
Okay, what should I factor?
I basically did it by graphing, but okay.
I see. Okay, we have x equals the square root of x, right?
Because I put the graphing calculator, and then I saw the intersections on there. But if you want to do it to by simplification, you could set them equal to each other.
Right, you're exactly right. So now we have x
Hello?
equal to square root of x.
Yeah.
Can we square both sides?
Yeah. To
Right.
get rid of the radical.
Right, to get rid of the radical. So now we have x squared equals to x.
So then it's going to be, yeah. So then it's going to be x squared minus x equals 0.
Good.
Then you take the x out.
Yes.
That's going to be x minus x times x minus 1. And then you set those x equals 0 and x minus 1 equals 0.
Perfect. X equals 0, x equals 1, right? Okay.
Yeah.
Right. Okay, great. Because usually...
Then you get the inner and the outer bound, which is 0 and 1.
That's right. Okay. So
basically the intersection.
Right. Okay. So great. And now, so we have this region. We have this region. So we're rotating this region over y equals to 1. So now, can you show us the other piece? Right. When we rotate about y equals to 1, can you tell us where is the other just give us an idea about the 3D object? Because after we rotate over y equals 1, we get a 3D washer.
Yes. So basically, the inner part where radical is gonna be the hollow part because it's a washer. So the outer one, that's gonna be the radius we're gonna find across. Get what I'm saying?
No, I'm asking you the 3D object, the 3D picture. Can you give us an idea about the 3D picture? We have this piece of region. Now we're rotating y equals to 1. Y equals to 1 is this line you're drawing, that dotted line. So after we rotate this piece, can you visualize the 3D object?
Yes, but it's like hard for me to explain, basically.
Well, just a piece of y equals 1, right?
Yes.
You get a symmetric region above y equals 1. Right?
Yeah.
I cannot draw over here.
Yeah, it's not allowing me to draw as well.
Okay. Then, right after you have this piece, you have 3D object. Then you can talk about, right, pi r square of the
It's
outer.
basically like a cone around the. So basically, y is like in the y equals 1 is like in the middle, and then you draw like a 3D.
Right, that's a
like
line
hard from you. Yeah, like it's gonna be like it's cone type 3D picture.
Yeah. Okay. All right. Okay. Keep going.
So basically now the formula is that you take the outer function, square it at times pi, and minus it by the inner function. And then when I simplify, I get 1 minus 2x minus x squared, and 1 minus 1 minus 2 radical x plus x. And when you further simplify, you get the negative 3 plus x squared plus 2 radical x. And then you take the antiderivative, and you get the function that I have on the second last line. Now you're gonna put your inner, the lower and the upper bound in. So when we put a 0 in, we're not gonna get, and it's gonna basically be 0. So which is pi minus, and then you substitute 1 in, and you get minus 3 or negative 3 over 2 plus 5 over 3. And then when you further simplify, you get pi over 6.
All right. So we see this is a pi. So we see this is the area of the outer minus area of the inner. Because we only want to get the solid, the volume of the solid.
Yes.
Okay. Good job, Elsa. Thank you.
Thank you.
All right. Anybody has any questions? Okay. Yes. Yeah. See your work. Go ahead. This is Karen's.
Do you hear me?
Yeah.
Okay. So it's given that y equals 1 over 4 x squared, x equals 2, and y equals 0. If you look at the graph and like the 3D object, you can see that the radius is going to be the x value. So I just isolated x from y equals 1/4 x squared, and it equals to x equals 2 rad y. It set the equal to 2, so I can find the intersection, and then the intersection should be at 2, 1. After that, you can see that the inner radius is the equation of 2 rad y, and then the outer is just 2. So you just do pi, and then the integral from 0 to 1, 2 minus 2 rad y squared, and then you just expand it to 4 minus 4y, and then find the integral, which is 4y minus 2y squared, and then just find that equation at 1, since 0 is just 0, and that should be pi times 4 minus 2, and that's just 2 pi.
Okay, I don't see how you find the limits, lower limit and the upper limit, 0 and 1.
When I after I it's on the bottom left. After I found x equals 2 rad y, I just set that equation equal to 2, because the equation on the right is just x equals 2, so they should be equal.
Oh, I see. That's how you get to the upper limit, y equals 1. Oh, I see. The lower, how do you get the lower limit?
Well, on the graph, it's just they just meet at 0, 0, because like the first equation is a x squared, right? So that means the center of the graph has to be at 0, 0.
I guess it's from the one of the conditions.
Huh?
Is it from here? Y equals 0.
Oh, I assume that it goes from 0 to 1, like it starts at 0, because at the equation x squared and times 1/4, right? If you graph it, the general shape the bottom of the graph, like where the lowest point is generally going to be at 0, 0, because there's no transformation going on.
No, it's from this, right? From y equals 0 equation. You're given 3 conditions. You're given 3 equations. One of it is y equals 0.
Oh, yeah. Oh, I
right?
thought you were talking about the x, sorry.
It's okay. So then, right, so you draw a picture over here. So basically, you could, the picture is just here. Right?
Yeah, yeah.
You could draw over here. Let's see. So now you're seeing, let's see. So we have pi r squared. And then you said that your r is 2 minus 2 radical y. Can you explain that? Why the radius is 2 minus 2 radical y?
So since we're rotating on the y-axis, right, the outside of the shape, which is like a weird like bowl, the outside of the shape will be, for at least the x value, will be 2, because that's where the equation x equals 2 is. And then you have to subtract the y value of 2 rad y, because that's the, like, the, it's hard to explain, but it's like the y value from like the center of the graph, or the like the
No, you're not
y-axis.
talking about the x, y value, right? You're talking about x value. This is the x value. The radius is x, right? So this is your r. Your r is represented in terms of x. One of the x is x equals 2. So this is the upper bound. What about the lower bound? The lower bound is this one.
Wait, lower bound is which?
This is this one. Can you see I was drawing for you? I was just following your.
Yeah, that's what I was saying.
Oh, okay.
Yeah, that's what I was saying. I'm saying that from the y-axis to the shape, right? That should be the x-axis of, I mean, not x-axis, the x value of y equals 1/4 x squared.
Okay. Maybe we're saying the same thing. So basically, this is your r. So this is your r. That's why we have 2 minus the x. What's the x? X can be written in terms of y. Okay, good. All right. Okay, thank you, Karen. All right. Anybody has any questions? Or anybody wants? Let's see. Malika is saying for the Washer method, don't we integrate along the y-axis? So the limit would be from 0 to 1. No, Karen is doing right. Karen is doing right. Okay, let's talk about it. I think you guys, probably some of you are ahead of me. I didn't really talk about the second method yet. And also rotate. Last time I only talk about rotating over x-axis, rotating y-axis. But again, it's all about figuring out the r, the radius, right? So the task is figuring out the radius. All right, let's go back. So to finish this section. So last time we talked about rotating with, we have a piece of region, and we can rotate that piece of region over x-axis, right? If I rotate this piece of region over x-axis, I get a symmetric region below x-axis. Right? I get this. So I get this piece. Right. Just imagine this piece is exactly symmetric to this. All right, I couldn't draw exactly like that. And the intersection or the level set is a circle, right? So this is a circle. So we want to cut along. If we rotate over x-axis, we want to find the area of this. Then we cut along x-axis, right? Infinite many pieces. Because why? Because we're finding the area of the circle. Right? Then we add up all the areas of this circle. Similarly, the idea is similarly when we rotate the piece with y-axis, we get this 3D object. Right? We get this 3D object. Okay, now let's talk about we're not rotating over x-axis or y-axis. We want to rotate with some other lines. So we see here we have pi big R square minus pi smaller R square, right? So this, if we do this way, we see we have hollow. We have something, so the 3D object is a hollow one. And we want to subtract out the volume of the hollow. But we only need to find the volume of the solid. So that's why we have this one. We have this subtracting. Yeah, this, let's check this one. So this one, we have this region. Then we can rotate this region over x-axis. We would get this 3D object. But the volume we want to find is only here. It's only this solid. The solid part. Only this and the bottom one. So the inner one, the inside is hollow. Sorry, I cannot show you. Okay. So the volume is made by this. Okay. So the inside, we see the inside hollow. It's not included in the volume. All right, so let's see this example. Example 5, find the volume of the solid obtained by rotating the region in this. Right? About line y equals to 2. So this is different now. Y equals to 2. Let's see a picture. So we have this piece of region. So this region is here. Right? So that's a piece of the region. Now we want to rotate this piece over y equals to 2. So this is a y equals to 2. This is a line of symmetry. So we want to rotate it. That means we get a symmetric piece. So here is what? Here is also we have y equals to x squared. So this point is 1, 1 point. One, 1. So this point is 1, 1 point. And so this is 1, this is 2. That means after we're rotating at this point, we have this rotating piece will be 3, 1, or 1, 3, I mean 1, 3. Because the x value does not change, only the y value, because we're rotating over this y equals to 2. So this point becomes 1, 3. And where is the piece? The piece is symmetric to the bottom one, right? So let's see. So here, okay. So we see the symmetric piece, right? So this is a region, and we're rotating this piece of region over y equals to 2. Over y equals to 2 line. So after rotating, we get this piece. And then, well, think about we are rotating this. So we get a 3D object. Now we want to find the volume of this solid. This is solid. So what do? Of course, we do pi r squared, right? But this is a washer, so we will do pi big R squared minus pi small r squared. So let me just write 1 pi. Right? We want to subtract out the inner one. So we do pi, so pi r squared outside minus pi r squared, the inner one. So again, the task is to find the big R and the small r. So this can be written as pi big R squared minus pi small r squared, right? Like we see here. So pi x squared, pi, well, think about this x squared is a big R squared, and this is a small r squared. So we need to find these two radii. Well, let's see this one. We're rotating over y equals to 2, right? We want to cut along x-axis because we cut vertically. We cut vertically. So we still set up our integration in x direction, right? dx. So we're cutting along x-axis. dx, right? We have this integration dx. So we need to figure out the integrand and lower limit, upper limit. Well, let's do one by one. Pi we can leave outside, right? Let's leave pi outside. So basically we want to find the big R and small r. So we'll put pi outside the integration. So the task is to find the big R, find the small r, and find the lower limit, find the upper limit. Right? Lower limit, upper limit, we see is obvious, or we can solve it, right? Y equals to x, y equals to x squared. Again, we set x equals to x squared. We factor out x. We have 1 minus x, x times 1 minus x. Oh, let's do this quickly. So set x equals to x squared. We let these two functions equal to each other. Then we move to the same side. We move 1 to the same side, so equal to 0. Then we factor out x. So we have x minus 1 equals to 0. So we solve this, we get x equals 0, x equals to 1. What we can see from the picture is obvious, right? So we find our lower limit, find our upper limit of x. We're cutting along x-axis. So this goes from 0 up to 1. Okay, if I'm confusing to anybody, so feel free to ask me, to stop me, all right? Ask me questions. Right? So we need to find, so we're cutting along x-axis. Right? We want to find out the area of this circle, then add up all those circles. Right? We have infinitely many circles, the area of the circles. So lower limit, upper limit, we want to find the intersection of those two functions. One function is y equals to x, another function is y equals to x squared. We set them equal to each other. Now we solve for x. X equals to 0, x equals to 1. The smaller value is our lower limit. The bigger value is our upper limit. But from the picture, we can see also, right, 0 to 1. So x value goes from 0 up to 1. Well, now let's figure out our r, big R. The big R we say is this curve, is this, what do we call it? Y equals x squared, right? It's y equals x squared. That's the outside. So this R, let me draw one. So let's say 1R for the outside one. For the outside one. Well, maybe, yeah, they should be okay, right? We see the big R. So this is our big R. It's from y equals to 2. From this line, y equals to 2. And to this curve, y equals to x squared. So we want to use 2 minus this x squared, right? So big R, let me write here. So big R equals to 2 minus x squared. Then let's see the inner R. The inner R is from 2 up to this straight line, y equals to x. Y equals to this. So let's write the small r. Small r equals to 2 minus x. So let's use this formula, pi times big R squared minus small r squared. So leave pi outside. So now we have our integrand. Our integrand is big R squared. Big R is 2 minus x squared, r squared, right? Big R squared minus small r squared. Small r is 2 minus x squared. So that's why we want to draw the picture. So this is our integrand. Big R squared minus small r squared. Or let's put a parenthesis. All right. Any questions? If anybody has any questions, stop me. Everything comes from this picture, right? So that's why when you show your homework, I ask you to draw the other piece. To draw this piece and to be, to make it visual for yourself, to see what's going on. So we're rotating this piece over y equals to 2. And then we have vertical, the section, so the vertical sections are circles. So we want to add up the area of those circles. The problem is we only want to find the volume of this solid. This is formed by this region, rotated by this region. So we need to subtract the volume of the hollow, the inside, the hollow. So basically we say we could visualize as two objects, right? So the one 3D object is made of outside, like a ball. And then the inside one is like a cone. It's like a cone, right? It's a part of the cone, let's say part of the cone, because it's a straight, because the sides are straight lines. Okay, that's why we have this pi big R squared minus pi small r squared. So we need to figure out the outside radius and the inside radius of the circle. Similarly, if we rotate over another line, right? If this piece, imagine this piece, we're rotating along, let's say maybe x equals to something. Let's say x equals to 2, all right? Let's say x equals to 2. We're rotating this piece along x equals to 2. We will see, so this, we reflect this point to this. Okay. Then this piece, we will get a picture like this. Right. Not exact, okay, but so what is this point? So if we rotate this region over x equal to 2, we would get a symmetric piece right here. So this point will be 3, 1. Right? And then where is the 3D object is this. So we would cut we would cut horizontally, right? We would set up the integration with dy. We would cut along y-axis, right? Because we cut that, we can look at the intersection, the section horizontally, because each section would be a circle. So we want to find the area of the circles, then add them up. So the idea is the same. Just instead of cutting x-axis, oh, I'm sorry, why do I still write dx, dy? We would cut along y-axis, right? And we see y value still goes from 0 up to 1, right? So the lower limit would be still 0. The upper limit is still 1. Right? What we can get from solve for the equation, right? So how to solve for the equation? We want to rewrite this equation. Y equals x squared. We would write, because this is in the first quadrant, so we would write x equals the square root of y, right? X equals the square root of y. Because now we need to find the radius. Again, let's write the pi outside. We need to figure out big R, small r. So in this case, what's our big R? Well, we see our big R. Big R is here, up to the straight line, up to this straight line. Right? I don't want this arrow. So this is our big R. From x equals to 2. So this is the line of x equals to 2. Right? So the big R will be from 2 up to this straight line. So that's outside radius. That's big R. So big R equals to 2 minus, oh, 2 minus y. Why am I writing x? That's where do we get? Because this line is y equals to x line, right? It's from here, y equals to x. And then with small r? Small r is from 2 up to this curve. And this curve, we want to write x in terms of y, where x equals the square root of y. So small r would be 2 minus square root of y. Okay, once we figure out big R, small r, you know, the integral will be big R squared minus small r squared, right? Big R squared minus small r squared. Okay, so that's why the text, you know, just 3 things in this case, all right? Figure out lower limit, upper limit, then figure out big R, figure out small r. So this is for getting volume of a washer-like 3D object. All right, any questions? So this is over, you know, over a straight line, x equals to something or y equals to something. Are the limits always 0 to 1? Or depends on the question, right? In this case, yes, right? In this case, always. In this case, it's from 0 to 1. You see everything happened in the first quadrant, and we draw this picture. Once we have this picture, we see that. Or we could solve from the setting the equations equal to each other, right? How do we do that? If we rotate along x equals to 2, fine. We want to rewrite y equals to square root of y, right? we would solve for this equation. So we write this one. So one function is y equals x, another function is y equals x squared. At y equals x squared, we want to write x in terms of y. So that would be x equals the square root of y. So we set this one equal to each other. We solve for y. We solve for y, we still get a y value. Then y would be equal to 0 and 1, right? Square both sides, we factor out, we get the lower limit, upper limit. For this one, is obvious. For some others, maybe we need to set them to equal, then solve for it. Okay, let's see more. Okay, anybody else has any questions? Okay, Malika has a question earlier saying, for the Washer method, don't we integrate along y-axis? Now do you see it depends on the situation, right? If it asks us to rotate over a line x equals 2, we cutting along y-axis. If we rotate over a horizontal line, so this rotates with a vertical line. Rotate with a vertical line, we cut along y-axis because y is a vertical line, y-axis. If we rotate over not x-axis, we rotate with a horizontal line. Horizontal line parallel with x-axis, right? So we would cut along x-axis. So it depends on how we rotate the piece. I hope that answers your question. Okay. Any other questions? Okay, let's see more examples. Let's see this example. So find the volume of a solid obtained by rotating the region in example 4 about x equals -1. All right, I talk about x equals 1 here, x equals 2. Now it's saying rotate this piece, or let's use a clear picture here. Rotate this piece over x equals -1. Well, where is x equals -1? So so this point is x equals 1. X equals -1. Let's extend this. Somewhere here, right? Approximately, right? This looks like x equals -1. Well, let's draw a line. Let's draw a dotted line. So this would be the line of symmetry. Oops. So here is a negative. Okay, this is -1. All right, so this is 1 because I see this point. This point is 1, 1. So the x value here is 1. So I measured about, a little bit off, right? It's off. But let's treat this one as a -1. So here is x equals a -1. Let's write here. X equals to -1. So this is x equals a -1 line. Well, let's draw this piece of region because we want to rotate over x. We want to rotate over x equals to -1, right? What's the distance? You see here. So 0, 0 become -2. So let's see. This might be -2. Right? So this point reflect over x equals to -1. I get this point, and this point I get somewhere here, -2, right? And the height is still, the y value is still 1. So I get this point, -2, 1. And this point will be -2, 0, right? Because this is -1, this is -2. So what is this piece? This piece I can draw like this. Please go straight. Give me an arrow. Oh. You know, just think this piece is perfectly symmetric to this piece. But the line of symmetry is x equals -1. So when we rotate, we get a 3D object, right? We cut horizontally. The intersections are perfect circles. Intersection are perfect circles. I'm going to draw only one of them. Think about this. Right? This will be the 3D object. But we want to only find the volume of the solid. So this is a washer, right? The middle part are hollow. So let me try to shade the region. Okay, so I'm trying to shade the region. Okay, so we're trying to find, you see, just convince yourself, right? You know, like this looks like a ball, right? Looks like a ball, and the thickness of the ball is this much, and we want to find the volume of this. So again, what do we want to do? We want to find, so we see the inner, we want to use the outside one minus the inside one, right? Let me just see. So we need to figure out the R. The big R up to here, from this x equals -1 up to this outside, up to this y equals x squared curve. So this is a big R. And what's a small r? Small r is up to this straight line. From -1 up to this straight line, right? So that's the inner radius, the small radius. The setup is still the same. So we will cut along. So here you see the circles are horizontal circles. Right? Horizontal circles we want to cut along y. So dy. We need to figure out the lower limit and the upper limit. And you know, again, we can set those equal to each other. You know, from previously we already know it's from 0 to 1. If you have a problem to see that, you can convince yourself, right? Set 0 to 1. And you know what, we want to find a big R and small r. The formula is the same. So we leave pi outside, because the pi is just a constant. So the inside is a big R squared minus small r squared. So the task is to find out big R and small r. Well, what's big R? Big R equals to, from this point, -1, or we could see from this, the outside, right? The x value. We want to, again, we want to write x in terms of y, right? We want to write x in terms of y. So this curve can be written as y equals x squared. Because it's in the first quadrant, it can be also written as x equals the square root of y, right? X equals the square root of y. So we could write r equals to square root of y root of y minus, let's do this, -1 minus square root of y. Oops. -1 minus square root of y. Or we could do square root of y minus -1. We would get square root of y plus 1, right? When we square, that would be the same thing. Let's do the other one. The other one, we don't have to deal with so many negative signs. So the square root of y minus -1 becomes minus -1 becomes plus 1. All right. So I'm not going to write minus -1. I'm going to do plus 1 because minus -1 is plus 1. So this is big R. Well, now let's figure out small r. So that's the outside R, big R. So what is a small r? Small r is from -1 up to this straight line, right? The straight line is x equals to y. So we can do y minus -1. Y minus -1 again is y plus 1. We figure out the big R, small r, which is, put into this integral. We would square the big R, subtract square of the small r. Okay, any questions? So that's why drawing picture is important. Right? Try to draw the picture. Try to draw the region. When we reflect it over a line, try to come up with a picture like this. Then it'll be easy to figure out the outside, the big R, the small r. So we have, right, so horizontal cross section, it's a washer with the inner radius of 1 plus y, or y minus -1, right? This 1 plus y comes from y minus -1. The outer radius is 1 plus square root of y, or square root of y minus -1, right? Because the line of symmetry is x equals to -1. So pi times the outer radius, the big R square, minus pi times the inner radius, the small r square. So this becomes our integrand. Then lower limit is 0, upper limit is 1. Right? And put the pi outside. The big R square minus small r square. Then the rest is just calculation. Right? Simplify the integrand. Then get this. Then just antiderivative, right? This is polynomial-like. Use polynomial rule for antiderivative. So we get this. Then we evaluate at 0, at 1. In the end, we get pi over 2. The calculation, I think, is easy for you. So only to figure out the big R, small r. Oh, the picture looks like this, right? But we're only calculating the volume of this. Right? Formed by this. So basically, we use the outside volume. Outside volume is like this. So this is the outside volume of this ball-like. Subtract the inside volume, the hollow one. Subtract the inside volume. Okay. All right, let's see more examples. So let's see this figure 12. Figure 12, this one shows a solid with a circular base of radius 1. So the base is a circle of radius 1. Parallel cross sections perpendicular to the base are equilateral triangles. All right, equilateral triangles. So parallel cross section, right? So, or I like to say vertical intersection. Vertical intersections, okay, are this equilateral triangles. Equilateral triangles means the 3 sides are the same. Okay, or 3 angles are the same, all 60 degrees. That's equilateral triangles. So what do we have to do? We want to find the volume of the solid. All right, let's see, how do we find the volume of the solid? So circle representation, radius 1 can be written as x squared plus y squared equals 1, right? Basically, we situated this piece, right, centered at the origin, 0, 0. The solid is base and a typical cross section at the distance x from the origin. So we're treating, so basically we're putting this piece, imagine this is a perfect circle. The base, right? The base is a perfect circle. So this is the xy plane. Then this is the z. This is z x-axis. So on xy plane, that's a circle, right? So this is x-axis. This is a y-axis. And this is a z-axis. So just thinking, so this, the xy plane, on xy plane, the base is a unit circle centered at the origin. So we call this base B, right? So this one, we can write y equals square root of 1 minus x squared, basically taking this upper semicircle, all right, upper semicircle. And lower semicircle can be written as y equals a negative square root of 1 minus x squared. So the base of the triangle ABC is this. The length of AB equals to 2 square root of 1 minus x squared. Right? Convince yourself, do a little bit of calculation because we have this, right? We have this equilateral triangle. And its height is the square root of 3 of y equals the square root of 3. Y can be written as a square root of 1 minus x squared, right? So can be written in this way. Then the area of a rectangle is a height times base times height divided by 2. So we get the area of the equilateral triangles written in terms of x. Then we get the volume. So now we're just adding all this area of these cross sections, right? So then would go, so from -1 up to 1, right? The x value. So this is because it's a radius of 1 unit circle. So x value cutting along x-axis, x goes from -1 to 1. Then we add up all those areas of these equilateral triangles. Then we do the calculation. So this has nothing to do with washer. This is not a washer kind. I don't know why they put this example here. But anyway. So let's see example 8. Example 8, find volume of a pyramid whose base is a square with side L and whose height is h. Okay, I think we're good with finding stuff like this. Okay, I'm going to skip this one. Okay, let's try some exercise. I think most of you already did very well because you're already able to do this about y equals 2, about y equals 1. I think someone showed 12, right? So let's try 13. Let's try 13. I only have 10 minutes. Okay, I'm going to leave you for next class then. All right, next class. So next class, let's see, 13 up to 18, and okay, good. 19 to 22 is only set up an integral for the volume of the solid obtained by what's given. Oh, it also asks to calculate. Okay, so we do. So I'm going to leave you more to practice. So to 22, to 13, to 22, let's see. So these ones, we need to graph them. 26. Okay. These ones are good too. So 27. All right, I'm going to leave you up to 28. All right. So let me leave you enough questions to. Oh, this is great. 32, 33. 32, 33 are very interesting too. 32 and 33. This is enough, right? You don't have to do every one of them, right? So 13 to 28, 32, 33, all right? If you think some other questions are interesting, all right, you could do also, right? That you don't really have to do what I assigned for you. Yeah. Cool. You know, if you're math majored or physics majored, maybe you want to try 50 also. Okay, next class, we're going to talk about this last section. Oh, already, actually, I have posted review sheet. I don't know if you see yet. I have posted a review sheet with approximately, 40 some questions. All right. So after we finish 7.3, we're going to start to review. Again, this course covered only 3 kinds of concepts: limits, differentiation, and integration. All right, any questions? Oh, thank you. All right, if no questions, I guess I'll see you next Monday, all right? Okay, good job, guys, today, all right? Good job, keep it up. Keep it up, we're almost done. Okay, bye. And yeah, some of you I worry about. Some of you need to present, all right? Try to present, I'll help you. I'll help you to present. All right, thank you, guys. Have a good weekend.